Hey everyone, so I'm one of, my drawing tablet is a bit, going a bit dodgy at the moment. I'm just going to try and restart it. But yes, I'm one of Dan's master's students working on some singular learning theory stuff. Uh, and um, so today for the supplementary session, I'm just going to go through some background um, algebra, uh, which will come up a lot in next week's talk. And so the focus of next week's talk will be about trying to replace analytic functions with equivalent polynomials. And so to sort of understand what's going there, some of the tools we'll use are just rings and ideals, and most importantly, today I'll talk about the Hilbert Basis Theorem. So anyone who's taken an algebra course, you will probably be very familiar with this background stuff. So I'm going to try and introduce it in a way that's not necessarily the most formal, but try and hopefully emphasize what the point is of each object or theorem, or at least what the point is for the stuff we'll be doing. So I'll start off just by defining a ring. So a ring, which I'll usually denote by this sort of R, is a set, and it's equipped with two operations. Which are called addition, usually denoted by a plus, and multiplication, which usually denoted by a dot, but sometimes, most of the time, we just omit that. And in particular, these two operations should behave roughly as you would hope. So I'll go through specifically what I mean by that, but sort of vaguely, they should work mostly like they work in the real numbers. I guess I should say that everyone sort of has their own specific definition of a ring, depending on what they're using it for. So sometimes people have different extra axioms, and other times they have less, but I'll just go through the ones which we'll be using. So what the multiplication and addition should satisfy is if you have three elements that are arbitrary elements of the set. Firstly, the addition should be associative, meaning that if you add A and B together and then add C, that should be the same as adding first B and C together and then A. And likewise, multiplication should be associative. The other thing is that addition should be commutative, meaning that you can just change the order that you write them in. So I think in general, in a ring, multiplication doesn't need to be commutative in all the rings that we'll be dealing with today and in next week's talk. The multiplication will turn out to be commutative. Okay, for some reason my drawing tablet only lets me use sort of the left 2/3 of the board, but I'll try and make it work. And also, so if you think about what happens in, say, the real numbers or the integers, there should be an element which we call 0, which does the same thing that 0 does for numbers. So specifically, if you add anything to 0, you should just not change that element, and there should be an element called 1, which does what 1 does in the real numbers, so that if you multiply something by 1, that should not change it. And then a couple more things. For each element A, there should be, oops, wrong letter. There should be an element which I call minus A, which makes, when you add them together, you get 0. I'll just go over to the next board to list out the last axiom. So the last thing is that the multiplication and addition should sort of work well nicely together, which just means that distributivity should hold. So if you add B and C together and multiply by A, that should be the same thing as if you just multiply through the brackets like that. And it should hold whether you multiply A on the left or right. So just going through some simple examples of rings. So I guess I already mentioned briefly the real numbers with its normal addition and multiplication forms a ring, it satisfies all those things. And similarly, so does the integers. Because yeah, if you multiply two integers together, you get back another integer. I'll just briefly mention like an example of a ring where the multiplication isn't commutative would be 2 by 2 matrices with real elements, because matrix multiplication doesn't in general commute. So for a slightly different example, we could consider all the continuous functions from the real numbers to the real numbers. And so multiplication and addition in this ring would be defined pointwise, meaning that if you have two continuous functions, then f1 plus f2 would be the function that sends x to f1 of x plus f2 of x. And similarly for the multiplication, it's defined in the exact same way. So the main type of ring that I've been using in my thesis is polynomial rings. So if you've taken an algebra course, you've probably seen this defined in a fairly more formal way. I think sort of the most, I guess, easiest way to, or quickest way to define it is to say, like, given a commutative ring, meaning that the multiplication commutes, the polynomial ring in one variable of R, it is written as just the ring and then x in square brackets, and that's the set of polynomial functions which go from the ring to the ring again. So an example of an element would be, for example, a0 plus a1x plus a2x squared, where these things a0, a1, and a2 are the coefficients, and they all come from the original ring R. And so I'm going to go run over to the next board. And so you can similarly have polynomial rings in as many variables as you want. So for example, you could have a polynomial ring with 3 variables, which is the set of polynomial functions from the ring cubed back to the ring. So when studying rings, a question that comes up, like if you're given a ring, how can you study or understand its structure? How can you sort of understand what it looks like and how it behaves? I guess, yeah, in a lot of maths, the way you try to understand an object, which is, or try to understand some sort of set, is to look at all of its subsets. So, for example, we've taken group theory. You're seeing that an important way to understand a group is to try and find all its subgroups. And so it's similar for rings. And so in particular, we look at a certain type of subset which has specific properties, and those are called ideals. So an ideal of R is a subset I, which satisfies the two following properties. The first one is that if you have two elements in I, then adding them together should also be in I. And the second one is that if you take any element in I and then any element, not just of I, but of the whole ring, if you multiply them together, that should keep you in I. So every ring, there's two specific ideals that appear in every ring, specifically the set which contains 0, because if you add 0 to itself, you get 0 again, and multiplying anything by 0 gives you 0. And the other ideal that's in every ring is the whole ring itself. Very ideal that looks slightly different could be in the set of continuous functions from R to R, where the ideal you could define an ideal as the set of functions which equals 0 at 0. Because if you add two of these functions together, the result will equal 0 at 0. And also if you multiply one of those by any other continuous function, it will still equal 0 at the origin.
Just a quick question.
Yeah, sure.
Are you considering just commutative rings, or are they left ideals or right ideals?
Yeah, so I guess I should say so. I guess for everything that I'll talk about, I'll just consider commutative rings, mainly because that's all I end up dealing with in my thesis, and then don't have to worry about the specifics too much.
Okay. To make it clear to everyone, I was referring to the RA multiplication.
True. Yeah.
Might be different if it wasn't commutative.
Yeah, that's a good point. So specifically what I've written out would be a left ideal, meaning that when you multiply on the left by anything else, you stand the ideal. And so in a non-commutative ring, there's a difference between left ideals and right ideals. And right ideals are basically the same definition, but they are sort of closed by multiplication on the right. So I'll just go over to the next board and give a sort of important type of example, which is if you have a finite set of elements, like A1 to AN in the ring, you can define what's called the ideal generated by these elements, A1 to AN, and so that's just written by putting those symbols in these pointy brackets. And so that's the set of all elements of the form V1, A1 plus V2, A2 plus Bn, An, where B1 to Bn are just any element of the ring. And so it's not too hard to see that if you add two elements of that form together, you get a third element of the same form. And also if you multiply one of those by anything else in the ring R, it still has that form. So a specific example of one of these would be in the integers. The ideal generated by 3 is a set for like n times 3 given n is in the integers. And so that's also, you could think of that as the set of all elements, that all integers that 3 divides. And so when you come across an ideal, the question that is often important to ask is, does it have, can you write it as an ideal that's generated by a finite set? And so in a certain type of a ring, so I guess, yeah, so then there's types of rings where every ideal is finitely generated or has a finite generated set. And that's what's called a Noetherian ring. So let's write it up there. So a Noetherian ring is a ring where every ideal is finitely generated. So yeah, so Noetherian rings are pretty important, and knowing that a ring is Noetherian tells you a lot about it. So I guess an important example is just the real numbers, and that's because the only ideals of the real numbers are just the zero set and all of R itself, which can be written as the ideal generated by 1. And so why is that? That's because, say, if you have an ideal that's not just 0, then you can take an element A, which isn't 0, and then 1 on A is in R. And so being an ideal means that 1 on A times A, which is just 1, is in I. And so then from that it follows that all of that I is all of R. And so that this is something that by the exact same argument holds for any field. Where a field is just a ring where you can invert the multiplication. And so I'll just run back to the first board to introduce the main thing for this talk, which is the Hilbert Basis Theorem. And so the Hilbert Basis Theorem tells you when a polynomial ring is an Noetherian. Okay, so what the theorem says is that if a ring R is Noetherian, then the polynomial ring is Noetherian too. And so this then sort of, this is a short argument, automatically implies that the polynomial ring in any finite number of variables is Noetherian as well. So I'm not going to prove this theorem. It's actually, the proof's not too difficult though. So if anyone's interested, I'd recommend just checking the Wikipedia. There's a couple of proofs, and they're not too difficult to follow. But in particular, what this implies is that if you have a sequence of, like an infinite sequence of polynomials, in this polynomial ring, that there exists some finite number j, so that the ideal generated by all of the fj's, so all of the infinitely many fj's, is equal to the ideal generated by just this finite set of the first capital J of those polynomials. And in particular, that means that for all n greater than this J, you can find polynomials, which I'll write A, J, N, I should use n to not conflict with the other n, so that that fm, so any polynomial after capital J, can be written in terms of f1 to fj, in particular, in this form. And so, so what I'll be doing in the main talk next week is studying what these, I guess, what are called quotients, the AMJs, studying what they are, and because there's infinitely many of them, you can form a series out of it, and studying where that series converges and is bounded will be important for trying to replace these analytic functions with polynomials. And that, this Hilbert basis theorem will come up a lot in that argument. And so that's all I have. So if anyone has any questions about any of that, feel free to ask. If nobody has any questions, I'll let everyone go and get some lunch.
Thanks, Spencer.
No worries. Thank you.